Swayam Prabha. Digital India. Educated India.
So let's see what happens if we have an achiral and symmetric starting material. Would that make a difference? Let's look at it. Here's a BH3 that goes on here and then gets oxidized here, and you get an alcohol. And in this case, you can get it here or here, and would it really matter? It won't really matter at all because it's achiral. It doesn't matter whether it's up or down because you can just take this and put it on top of this. So therefore, this is going to be achiral. What happens when we put a bromine? So in this case, you have a three-membered ring. So a lot of these have got three-membered ring. This, over here and here. All of these have very similar reactions. When you have that three-membered ring holding on the top and then attack from below, you will see they have very similar outcomes in terms of stereospecificity, regioselectivity, and so on. Let's look at it. Here's your bromine rollover, and you're getting this. Now, are these the same thing? If I flip this 180, no, they're not going to superimpose. So therefore, these are non-superimposable. Are they mirror images? Sure they are. If you put a mirror here, it's going to reflect this exactly. So these are very definitions of enantiomers. And there is really no selectivity. There's no electronic or steric bias here for one over the other. So no stereoselectivity, no regioselectivity, just stereospecificity, and that's going to be anti. And here I'm just going to put a legend here. A is anti and S is syn. Now enantiomer 1-to-1. Over here you're going to have the oxygen attack either here or here. So you would have this, plus you would have it where you'll have your OET here and your bromine here. And would that make a difference? Let's draw it out. So this and this, plus let's just draw it out and see if they're the same thing. So here is another one where, let's say, your your ethanol attacks here, and you'll have a bromine roll over, and you will have a OET here after deprotonation, and a bromine on top. Now, is this different from any one of these? Let's look at it. If I take this and rotate it, you're going to get this. So this will be the same as this, same as that. All right? So it doesn't matter whether it attacks here or here, the products are going to be the same. And both of these, are they the same? Are they mirror images? Are they superimposable? Let's look at it. If I take this, flip it over, your OET is going to come down here, and your bromine will go up here. So they're not going to be superimposable. That's the only way you can superimpose them. And what if I take the mirror and put it here? It's going to exactly reflect this. So therefore, both of these are mirror images. And you can see this is a mirror image of this. So it's a 1-to-1 enantiomer. And it's the same here. Initially, you had a chlorine here that had a three-membered ring, and then your acetate or acetic acid attack that over here or here, and you're going to get both of these. You can have the chlorine form up or the chlorine form down. Both of them are going to be identical because they are superimposable. And then when you attack with the acetic acid, you can attack here or here, and that also wouldn't really matter. It's almost the identical case as above. So therefore you're going to get these two, and if I put a mirror plane right here, you're going to get reflection, and you're going to get this one, right? So these two are going to be mirror images of each other, and they're going to be enantiomers 1-to-1. All right, so whenever you have a triangle or a three-membered ring, a syn addition followed by an anti-addition, you can see very similar stereospecificity. Here's another one. Here's your MCPBA in a aprotic polar environment, and you're just going to get this. This is exactly the same as this. You can just take this, rotate it, and they're going to be superimposable. So there's just one product over here. And if you open this up, now it becomes a similar scenario to this, where you have a three-membered ring and you're getting backside attack. So when you do that over here, you can attack here or here and then get protonated and deprotonated, and you will get this. Now if I take this, you can see if I put a mirror here, you're going to reflect this molecule as this. Now, are they identical? If I take this and flip it over, they're not really going to go over there. Okay, so therefore, this is not going to be a situation where they are identical. They are going to be enantiomers. In this case, as I said before, you have a mirror plane, and they are achiral. They are both identical substances. Here's another one where you're again forming a triangular or three-membered ring and attacking from below, and you can attack it here or here. Equal opportunity because there's really no steric bias for either position. Same story here, three-membered ring, triangular intermediate here, and opening from below. So like a syn addition first, followed by an anti-addition. What would you expect? Take a wild guess. You've done this many, many times, and you're seeing a trend. Well, this is more of the same. You're doing a epoxide attacking from below with an anionic nucleophile, which is, in this case, it really doesn't matter because the steric is the same at both ends. It's not going to prefer one over the other. There is no regioselectivity. There's no stereoselectivity. It's only stereospecific. So over here, you're seeing another scenario here, which is very similar to the one above here. Here you had protic, and here you have aprotic and anionic. Now, if they were substituted differently, that would be a whole different issue, and we saw that earlier. So these are also enantiomers. So you're seeing the same trend over and over again. A three-membered ring followed by an anti-addition gives you enantiomers. Here's another one. Here we have a mercuric acetate and followed by sodium borohydride. Here you're only having a hydroxyl on one of the carbons, and this is completely achiral because we have a center of symmetry. The other end of your alkene was hydrogenated. Therefore, you're not going to see a chiral center here. It's just not chiral. So over here, your hydrogen can go this end or this end. It doesn't really matter. You're forming a carbocation. Really, if I remember rings, you can expand to a 6, so there won't be any ring expansion. It's not going to contract to a 4-membered ring from a 5, so therefore you're not going to have any rearrangements here. You're going to just get your iodide or bromide or chloride attack above or below, and would it really matter? Not really. If you take this and flip it over, it's going to superimpose on this, so they're the same molecule and they're achiral. So you are seeing that if you have attack on just one of the ends with a nuke group, then it's going to be achiral. Same here, sulfuric acid with water, you're forming a carbocation. Again, even if you put this hydrogen over here, it's still going to be secondary. I mean, the carbocation can go around the ring, but it's all going to be secondary. There's no possibility for really a stable ring expansion, and you're going to get hammered on top and bottom with water. To take this and flip it over, they are exactly the same. You have another achiral. So you're seeing that a trend emerge here. Hydrogen and platinum, you're just going to take that beautiful alkene and just completely take it off. So that is just going to be achiral again. So over here, you took this beautiful pi bond, broke it up. You got an sp2, sp2. Here's an sp2, sp2, all flat. CH2s, those are achiral. The whole molecule is achiral. So you don't really have to worry about enantiomers, diastereomers, and so on. All right, here's KMnO4, same thing. You can do hydroxyls on both sides, up and down, but they have a mirror plane of symmetry, which means you can take these roll over, superimpose, same molecule. So therefore, that's achiral. So we talked about how MnO4 and OSO4 close cousins. You have RuO4, ruthenium tetroxide, IO4, so many things that have these tetroxides. And if they're attached to alkenes and do diols, they're all going to give you the same result. Diol is going to be asymmetric if you have hydrogens on both ends or identical groups on both ends. It doesn't have to be hydrogen. It could be methyls on both ends or ethyls on both ends. As long as you have the same group here and here, you're going to get exact same results. So this is also achiral. So having gone around the entire wheel, let's talk about what would happen if I take this molecule over here and make the molecule chiral to start with. What would happen? Would you see the same results or would you have different results? Let's look at